Hi girls, welcome to class. So today we're going to look at chapter 4.3, the chain rule. So again, this is just another tool that we can use, another method in finding derivatives for a specific type of function. So today we're going to look at the chain rule, and the chain rule is really helpful for type of composite functions. So we're going to use the chain rule when we have what we want to think of as a function within a function. For instance, you've seen composite functions in like Algebra 2 and Pre-Cal, where let's say we had g of x was, let's say x plus 5. And let's say we had f of x, and we'll call f of x x cubed. Okay? So if we want to find f of g of x, right, then we would go up to f of x, and anywhere we see an x, we're going to put in g of x, right? So this actually we think of it as f of x plus 5, and it would become, final answer for this composite would be x plus 5 cubed. Right, so that would be f of g of x. So now we find a lot of these functions in calculus, and when we want to take their derivative, we use what we call the chain rule. And what the chain rule looks like is when you have a composite function, just like g of h of x, we're going to take the derivative of the outside function, leave the inside function the way it is, and then multiply it by the derivative of the inside function. Okay, so again, looks kind of complicated, but let's try some examples. So basically, we're going to use the chain rule anytime we have like a polynomial taken to a different power. Okay, so taken to an exponent. So again, if we think about the outside function here, we could think about the outside function as x to the 5th, right? If we thought about all of this as an x to the 5th power. So to take the derivative, let me get rid of that. So to take the derivative of x to the 5th, we would take 5 times x, but we're not going to write it, and then subtract 1 from our exponent to the 4th. So now we do that exact same thing with this function. We just bring the 5 out, we keep the inside function as is, and subtract 1 from the exponent. Okay, so that is the derivative of the outside function. Now we multiply it by the derivative of the inside function. So the inside function is 2x squared plus 5x plus 1, and the derivative would be 4x plus 5. Okay, so we have the derivative of the outside times the derivative of the inside. Now to clean it up, the only thing we can really clean up here, you never want to distribute into a parentheses to a power. Okay, so we do not want to distribute this 5 into this parentheses taken to the 4th power. Okay, so the only thing we can combine is we can distribute this 5 into this parentheses because it is just to the 1st power. So we can say 20x plus 25 times 2x squared plus 5x plus 1 to the 4th. And that is as neat and clean as we can get it. Okay, now let's try another one. So again, looking at number 2, again, the outside function we can think of as x to the 7th, right? And the inside function we can think of as 3x to the 3rd plus 4x squared plus 8x minus 2. So when to take the derivative, we take the derivative of the outside function, which is going to be bring the 7 down in front, reduce the exponent by 1. So that's the derivative of the outside, and the inside at this point stays the same. Now we multiply that by the derivative of the inside function, which is going to be, which we use the power rule, so 9x squared plus 8x plus 8. And we're done with the rule. Now, to clean it up, we can distribute that 7. Again, we don't want to touch anything to the 6th power because that would actually be taking 7 to the 6th power, and we don't. That's not part of the problem. So we can distribute that to this parentheses. So we get 63x squared plus 56x plus 56. So I've distributed the 7 over here, and then times 3x to the 3rd plus 4x squared plus 8x minus 2 to the 6th. Okay, now let's try another one. So again, we look at this one. It's a composite function. We can think of the outside as being x to the 3rd, right? And think about the inside being x to the x squared minus 5. So the derivative, we take the derivative of the outside first, which would bring down the 3, subtract 1, and make it squared. Bring down what's inside, x squared minus 5. Then multiply by the derivative of the inside, which in this case just becomes 2x. So now, to clean that up, again, we don't want to mess with anything to the 2nd power, so we can multiply those two, and we get 6x times x squared minus 5 squared. And we're finished. Okay? Now, there, like everything we've done in this class so far, it gets a little bit more complicated when we introduce radicals and fractions. So when we look at this one, everything's under the radical. So first, let's rewrite that. Again, I'm not taking the derivative right here. I'm just rewriting this whole expression to be to an exponent, which in this case our exponent is going to be 1/2. Okay, so again, this was just a rewrite. Now I go to the derivative, and again, now in this outside function, I'm going to use the chain rule, and the outside function here, I want to think about it as x to the 1/2. The inside function is this piece. So when I take the derivative of the outside, I've got 1/2, and then whatever's in parentheses to the minus 1/2. And then the derivative of the inside becomes 6x squared plus 5. No, I'm sorry. Shoot. Sorry. I don't want to start over again. So I don't scratch that, girls. So I keep the inside the same. 2x to the 3rd plus 5x minus 11. Now I take the derivative of the inside, which is 6x squared plus 5. So now, to clean this up, it's a little bit trickier. So first, let's rewrite this to get rid of this negative exponent. Okay, so the negative 1/2 means that this whole expression needs to go underneath. We're going to keep the 1 on top, bring the 2 down, and also bring all of this down. So I get 2x to the 3rd plus 5x minus 11 to the 1/2. So I've just addressed that negative exponent by bringing it down. And now this 6x squared plus 5 is a positive exponent, right? So it stays on top. So I get 6x squared plus 5. Okay? And now that I'm going to rewrite it to be a little neater, but I really can't do anything else with it because I can't. If I could take out a 2 up on top, then I could maybe cancel it out with this 2, but since I can't divide 5 by 2, I really can't do anything with it. So final answer here is going to be 6x squared plus 5 over 2 times 2x to the 3rd plus 5x minus 11 to the 1. Okay, so you have to be careful on your cleanup. Okay, so let's try another one. So again, first thing I'm going to do here to get rid of, or to rewrite that radical. So again, I'm not taking no calculus yet. I'm just rewriting to the 1/2. Now my outside function is x to the 1/2. My inside function is 21x squared minus 8x. So when I take my derivative, I bring down the 1/2. Subtract the exponent by 1, so I'm going to have negative 1/2. Then I keep the inside function the same. 21x squared minus 8x. Then I multiply by the derivative of the inside function, which is going to be 42x minus 8. Okay? Now, to clean this up, let's see, let me go back to blue. So now to clean this up, I've got my 1/2. I'm going to take this down. So 21x squared minus 8x to the positive 1/2. And I'm going to bring this over. So 42x minus 8. Okay? Now I can, 42 and 8 are both divisible by 2, right? So actually now to reduce it, I could write it like this. So I could take out a 2 on my numerator and say 2 times 21x minus 4, over 2 times 21x squared minus 8x to the 1/2. So I wrote it with a GCF, and now it's obvious that the GCF cancels, so my final answer is this. So again, you just have to be careful simplifying it, that if you're going to reduce it, you need to make sure that you actually can take out that GCF, that it comes out of all the terms in the numerator. Okay? Okay. So now we've done normal exponents, we've done fractional exponents. Now we're going to look at negative exponents. So you can see a pattern here. So now if you look at this, again, we could use the quotient rule here, okay? But we really don't have a variable up top, so we really don't have to think about it as a function over a function. So what we can do here is we could rewrite it. If we treat it as a quotient rule, we'd get the same answer that we're going to get now, but on these, a lot of times it's easier to do a rewrite, and by rewriting it, we're just going to take this up top and make it negative. So we can rewrite that to 2x plus 5 to the negative 6th, right? I mean, we could show that it's being multiplied by 1, but it's really not necessary. So now we rewrite it with that fractional exponent. Now we have an outside, we can use the chain rule, because our outside function is x to the negative 6th, and our inside function is 2x plus 5. So now if we take the derivative of the outside function, we bring down the negative 6 and subtract 1 from the exponent, gives us negative 7. Inside stays 2x plus 5, and then the derivative of the inside is just 2. So now if we clean that up, the 2x plus 5 to the negative 7 goes down and becomes positive, and I can multiply the negative 6 times 2, and I get negative 12. So negative 12 over 2x plus 5 to the 7. Okay. Try another one here. Again, first I will rewrite and make it x squared minus 3x to the negative 7. Now my outside function is x to the negative 7. My inside function is x squared minus 3x. So I take the derivative, I get negative 7, and then change the exponent to negative 8. Keep the inside. Multiply by the derivative of the inside gives me 2x minus 3. Now to clean it up, I'm going to keep the negative 7 out front. I'm going to take the x squared minus 3x downstairs and make it positive. And then I've got the 2x minus 3 on top. And now I can distribute that, so negative 14x plus 21 over x squared minus 3x to the 8th. Okay, now I want to add a problem onto here for a second, because I just realized something I haven't shown you guys. So let's make up a new problem here. Let's call it f of x equals, and let's say it's 9 over x squared plus 2x to the 5th. Okay, so I just made up that problem to show you guys another way to do it. So again, even though there's not a 1 up top, there's still no variable in the numerator, so we can still rewrite that to be 9 times x squared plus 2x to the negative 5. So I've kept the numerator and just still brought up the denominator and made it negative. So now when I look at this, my outside function, I can still use the chain rule for this and think about it as x to the negative 5. And actually you can think about it as 9x to the negative 5. So, and then my inside function is x squared plus 2x. So now when I take the derivative of the outside, I'm going to get negative 45, and then the inside function, and subtract 1 to the negative 6, and my inside function is x squared plus 2x. Now I take the derivative of the inside, I get 2x plus 2. And now when I clean that up, I'm going to get negative 45 on top, and the 2x plus 2, which I'll distribute here in a second. And then the x squared plus 2x comes to the bottom, to the positive 6th power. Now if I distribute that negative 45, I get negative 90x minus 90 over x squared plus 2x to the 6th. Okay, so now if there were variables in the numerator, I would want to use the quotient rule. With there just being a constant, I can just rewrite that with a negative exponent. Okay? All right, now there's 2 left here. So I'll tell you what, let's go ahead and work through this one. So again, this is a fractional exponent, but it's not just a square root. It's a 3/2. So again, same rule applies though. So the outside function here, we can think about it as actually 12x to the 3/2. The inside function, we can think about it like that. So now, when I take the derivative of the outside, I'm going to show every step here. I'm going to keep my 12 out here. I'm going to bring down the 3/2. Subtract 1 from my exponent gives me 1/2. And my inside is 4x to the 4 plus 5x. Take the derivative of the inside, I get 16x to the 3rd plus 5. Okay? So now, to clean that up, I am going to do a couple things here. Okay, so everything's going to stay up top, right? Except this right here, I can think of that as 6 times 3 is 18. Right, so you could either reduce it like I did, or you could have done 36 divided by 2 is 18. You know, either way, this should come down to 18. And then, so again, if I show my steps here, this becomes this. That stays the same. And now, though, I can combine, I can distribute the 18 into the 16x to the 3rd plus 5. And 18 times 16, pretty sure is 288, if I just cheated the right way. So that's 288x to the 3rd plus 18 times 5 is 90. And then times 4x to the 4th plus 5x to the 1/2. So I never can, when I have an expression taken to an exponent, you never want to distribute inside of that. So this, like I said, this piece has to stay the same. Okay? We can only, eventually we might reduce it with another of the exact same value expression inside, but we won't get to that right now. So final answer. Okay, and this last one is actually a pretty simple one that we'll just do together real quick. So, sorry about that. So again, it's just a normal chain rule. Outside function is x to the 8th. Inside function is right here. So the derivative would be 8 to the 7th. And we've got 4x to the 3rd plus 2x squared minus 7x. We multiply the outside by the derivative of the inside. Move all that over. So we multiply by 12x squared plus 4x minus 7. And then final answer, we distribute that 8 to 12x squared, which is 96x squared plus 32x minus 56, and then times 4x to the third plus 2x squared minus 7x to the 7. So again, final answer. Okay, so I think that's all the notes. So anyway, that is chain rule, and again, it is applicable when you have a function within a function, and it works for any functions within the functions, no matter whether the exponents are fractions or negative. So anyway, do your best with the assignment, with the homework, and I will see you girls on Monday. Thanks. Bye. Have a good weekend.